Wastewater Treatment 101 session. I am Kathleen Esposito. I work for the New York City Department of Environmental Protection in the Bureau of Wastewater Treatment. I am the agency lead on the feasibility study to consolidate wastewater resource recovery facilities onto Rikers Island. I'm so pleased to welcome so many members of the Closed Rikers and Renewable Rikers community today, as well as members of the Rikers Island Advisory Committee and some of our partner agencies on this work, including the Mayor's Office of Climate and Environmental Justice, the Department of Sanitation, DCAS, Department of Corrections, and the Mayor's Office. So DEP and MOCEJ, which is the Mayor's Office of Climate and Environmental Justice, are leading the two renewable Rikers studies, one for wastewater consolidation and one for renewable energy. Our teams are committed to thoughtful community engagement and participation for our studies. And when we connected with some of the renewable Rikers advocates on community engagement over 1 year ago, which is very hard to believe when I looked back, we had discussed the highly technical nature of the two studies and agreed that many of the folks involved would benefit from introductory sessions on wastewater treatment and energy. And so here we are today, kicking off with a primer on wastewater treatment. Today's Wastewater 101 session will be given by Pam Alardo, and I'd like to take a few moments to introduce her. Pam has been an environmentalist since the 3rd grade and has grown to become a leader in the wastewater resource recovery field. Her career began as a water and sanitation engineer in the United States Peace Corps. From there, she worked with the Washington State Department of Ecology, then moved on to the King County Wastewater Treatment Division in Seattle, and now in her current role as the Deputy Commissioner for DEP's Bureau of Wastewater Treatment, all while keeping involved internationally in water and sanitation programs. Pam has a professional engineering license in 2 states and enjoys being a licensed grade 4 wastewater treatment plant operator. Before handing the presentation over to Pam, I just have a few housekeeping items to review. First, please mute your lines. We have a lot of attendees here today, and I'm sure a few more will be dropping in, hopefully. Next, please hold your questions until the end. You can definitely feel free to type questions in the chat as we go. However, we'll hold off on responses until the end. And lastly, this session is being recorded for the benefit of those who cannot attend and for future use. We're working on a website and we'll add a link to the session in the near future and keep you updated on that. And with that, I'm proud to give you Pam.
Hey, hello everybody, good afternoon. I see that there's a pretty big group here. I want to thank everybody for joining. I'm going to proceed in this session as I would when I give a tour of a treatment plant, a wastewater resource recovery facility to the general public, assuming people have not visited a wastewater plant in the past and don't know much about its function. One of the things I start out saying when I give a tour or even talk about what we do is I ask this question, which is, who has used the toilet today? And surprisingly, when I ask people to raise their hands, hardly anybody does. So one of the goals here is for people to, first of all, get over that, understand the importance of managing wastewater and human waste, and educate people about the value of the services we provide, not just in the strict sense of treating wastewater, but also in the environment, the circular economy, creating sustainability and the value of green energy and green products that come from these wastewater resource recovery facilities. I also wanted to comment on the group here. I know that there's people from a diverse set of backgrounds. I really appreciate this as a kind of a unique opportunity and also a unique situation in that we have advocates for criminal justice, we have social justice advocates, we've got, you know, the environmental community, you know, kind of the standard water quality interests from people. There's housing advocates and, you know, a whole range of different diverse universe that's being brought to the Rikers, the closed Rikers, and the renewable Rikers aspect. So I think this is super unique, and it's a huge benefit to that level of diversity in making the best decisions for the city. And this is really a generational decision, a generational analysis, and a, you know, basically setting the trajectory for 100 years for the wastewater utility and wastewater resource recovery services for the city. So I wanted to recognize that level, the unique, diverse nature of who we are here, which gives us all the opportunity in front of us to learn from each other. And this, you know, what we're going to talk about is the basics of wastewater and this feasibility study, which is a very technical document, but it really is a community project. And this community project focuses not just on the technical aspects, the financial cost aspects, but the environmental and social and equity justice aspects, which are baked into the process of analysis and going forward from here. And, you know, just on a personal note, you know, I'm a regular person, a wastewater engineer, an environmentalist, a wastewater treatment plant operator background. And you know, in my life, I hadn't interacted with the the criminal justice community until I had a family member who unfortunately ended up in jail. And that was tough on all of us. And it was not in Rikers Island, and it wasn't even in this state, but it was a big learning curve about how the criminal justice system impacts individuals. And, you know, aside from the jail experience, coming out and the kind of challenges people face in terms of restitutions and limitations on their ability to get employed, and that whole paradigm was really eye-opening to me. And I want to acknowledge and appreciate that this project has to respect that and set up opportunities for us to continue to alter that path and create opportunities for people that otherwise they would be left without. So I think that's an important component of what we're doing today. And I can go on, but I won't. But I just want to acknowledge the unique level of diversity and interest we have here and want to move us all together on the same ship to the future. So with that, let's get started. And I'm not controlling the slide, so we're going to go for it. All right, this is what we're going to talk about. Oh, I'm just going to give you the outline. Okay, we already did this. Okay, this is what we're going to talk about. So I'll just talk about it. Let's go. So a little background about the Department of Environmental Protection in New York City. We're not just about wastewater, and most people know about us as a water supply agency. So we do bring the clean water from upstate to New York City, an amazing feat that's been going on for 150 years, and about 100 plus years worth of wastewater treatment. And that is the niche that we fill here, and I'll talk about that in a lot more detail. But just to round out DEP, we also do enforce air and noise and other local environmental codes for the city at large. We're about 6,000 people in total. 1,800 of that is the wastewater division. Real basic, why do we treat wastewater? Well, first and foremost, we are a public health agency. Here's a short list of diseases that are prevalent if you don't manage wastewater properly. I like this little graph because on the bottom it shows general death rates per population of 1,000, Berlin, Paris, New York, general death rates. And then New York City actually was a leader in typhoid deaths in the early 1900s. And this is the reason we started to build wastewater infrastructure. And we've taken that further of not just preventing disease, but I think if you click, we'll get something else. which is really to protect public health, like I mentioned, and enhance the environment. And that environment, the recipient of this work has been the New York City harbor waters. There's actually whales and other marine mammals coming back to our waters. It's a testament to the work that the collection and treatment of wastewater has done, in that it has been able to reestablish some of an ecosystem that was lost long ago to create an environment so that these healthy creatures want to come back and live with us in our adjacent waters. Okay, so a little bit of history. You can imagine, before there were treatment plants, there were people. And, you know, when people lived in dispersed populations, managing wastewater was not that big a deal. People can stay away from a wastewater deposit, so to speak. But when people started living together in cities, it became a problem. Not only did you have human waste, you had horses, you had, you know, animal waste, you had, you know, cows or whatever you may have in a city, and there was a lot of contaminated water because of that. And so the early sewers, not just in New York City, but also in the any city actually, the original wastewater plants were just to put pipes in the ground and get it away from people and get it to the nearest water body. Totally made sense. Get it away from people. We determined that it was a disease-causing problem, and that worked great until there was enough of it that the nearest waterway was not a solution. And over time, that polluted water became noticeable and became an actionable item. So in the 1897, I believe, was the first time the city put in a treatment plant. Is this the next slide we're going to get here? Oh, no, it's not. Not yet. The next slide is, okay. So we did put a new plant in 1897, but the first beginning of our sampling of the harbor waters was actually in 1906. And that means we've got 100 and almost 20 years worth of water quality data. And these, the data from back then found numerous dead zones, nowhere close to the ability for it to support a marine ecosystem the way it does now. So back then, at the turn of the previous century, is really where the city started to think about how we're going to treat and manage sewage. And then it became a plan. In 1886, I stand corrected, we started to treat wastewater for the first time. Coney Island, the places where people like to go swimming, was the first target for obvious reasons. The earliest treatment plants were basically retention, a little bit of settling, and disinfection. And that made a huge difference. It helped disrupt the pathways of disease to humans. So that whole area of Jamaica Bay, or the south end of our service area, was the early targets, you know, well before anybody thought about Clean Water Act or anything like that, entirely driven by prevention of disease and preserving public health. Okay, so then over the next 100 years, the city started to build wastewater infrastructure. So today we end up with 14 wastewater resource recovery facilities all around New York City. The little map to the right shows the yellow dots are the various wastewater resource recovery facilities, and the colors show the areas in which each of them drain. So you can see that there's various sizes of plants in terms of the flow they may take from the surrounding communities. And today, that total capacity for the whole range of treatment plants is 1.8 billion gallons a day, and that is a dry weather design capacity. I mentioned that the early wastewater infrastructure was just getting the pipes in the ground in order to get contaminated water away from people. And when we built the treatment plants, and this is the same of every city in the world that was big enough to even put drainage in the beginning, the treatment plants were built to disrupt, to collect from that existing drainage system. And therefore, I'm sorry, I'm hearing some background noise. And therefore, we have a combined sewer in much of New York City, which means not only do we take the flow from homes and businesses, the typical wastewater flow, there is about 60% of the city, if not more, is combined in that it collects flow additionally from streets, runoff from streets. So that is a remnant of the collection systems that were put in early. So today, I talked about the 14 facilities that we have. There's basically, we're the biggest wastewater utility in the United States. We have about 1,800 people, except for the fact right now we've got a lot of vacancies, so we're quite a bit less than 1,800. I think we have about 200 people vacant. We have, and I'll talk a little about dewatering facilities, what that means. We shouldn't ignore the fact that we've got to get the flow to the treatment plants. And so therefore we have 96 pumping stations that are part of that extensive collection system. I should mention that there's over 7,000 miles of wastewater pipes in streets. And we also have a number of regulator stations, almost 500. These are points that actually help regulate the flow and get it to the treatment plants, and also are potential areas where we would overflow if we need to in very high storms. We also have a series of combined sewer overflow storage facilities as well as laboratories. And I'll talk a little bit about these inner harbor vessels, these boats that we have in the process. Does that come up? I can't remember if we talk about that later, but I will if it doesn't pop up again. But it's a little unique thing about New York City. I say that I have my Navy here, and because we do utilize boats to transfer some of our solids to the final treatment for dewatering. But let's continue. One of the things you might notice when I had a picture of a whale is that the water is clean enough for such marine life to rebound and come back to the city. So if you look at another thing we're blessed with is 100 plus years of water quality data. So if you look at the data from the 1960s to today, you see a big change in, and this is fecal coliform. There are other parameters that we monitor for. In fact, we could do the same thing for dissolved oxygen, which is a health indicator for receiving waters. But you can see that it was a big problem in the 60s. Again, the early plants were targeted to Jamaica Bay for primary contact with individuals. And in the 1930s, a number of other plants were built. And finally, North River was the last plant that was constructed in the 80s. So it took a long time for treatment plants to get up and running and change this dynamic of the receiving water quality. The Clean Water Act passed in 1972. So the difference between 68 and 85 is the federal mandate to treat wastewater. And it wasn't just to treat wastewater, it was to treat wastewater to secondary standards, which include not just a physical treatment process and disinfection, but added a biological treatment process, which actually consumes organic waste from the waste stream. And that made a huge difference between the 70s to the 80s, and then over time you see the improvements into this century. One of the things I like to point out in the map to the far right is it looks pretty damn good. Excuse my language, but it looks really good. You see a lot of blue. You see that the water is much cleaner. The challenge we have today, and it's probably impossible to see on this screen, is that there are a number of small water bodies, which used to be before the city developed and filled a lot of wetlands and filled a lot of meandering streams. Those used to be actual streams that were disrupted hydraulically, and the water quality is very challenging in those small streams throughout the city. And so the plans we have now to address the remaining water quality issues are very focused on those small tributary type streams. So let's get into the fun stuff. My goal here is to make all of you wastewater enthusiasts by the time we close this Teams meeting. And like I told you, I asked people who's used the toilet today. My goal in life is that everybody knows what happens after they flush. because it's important for your public health. It's important if you understand what you're paying for and your rates for water and wastewater management. It's important for you to appreciate what is done, and it's important for people to understand that we take care of it so you don't have to. And for everybody who's on this call, if you have not actually visited an operating wastewater resource recovery facility, you are all welcome to do it, and we will set you up with a tour. We can, we have 14 to choose from. Newtown Creek is the one we use most frequently because it's kind of set up for visitors, but it's important to, get the look and the feel and the smell of a wastewater treatment process. I'm going to talk a little bit more about odors in a minute, but I wanted to give you the very high level description and get into a little bit of cool detail. So we are a factory. This thing that sits in the middle is a factory. And like every factory, we take in raw materials, inputs. So our inputs are residential and commercial wastewater, industrial wastewater, and stormwater for a big chunk of the city. Goes to this treatment plant. This is the processing manufacturing facility. And within that, we create resources that we reuse. We clean water enough to use again within the system, so we don't have to increase our use of potable water. We create electricity and heat from the processes that are indicative or integral to wastewater treatment processing. We also have a side stream where we could take food waste, and I'll talk a lot more about that later, but that doesn't go directly to the treatment plant. And then we make products. Like every manufacturing facility, we make products, and these are valuable products. The first and foremost is clean water. In that we put 3 billion gallons a day up to back into the harbor waters and have been responsible for those improvements like I talked about. Fit for purpose water or recycled water, we can use it internal to the plant, and we could also use it for irrigation and non-potable use external to the plant. I got to say, in New York City, because of the quality and quantity of the water supply, there is not a huge market for this reused water. In places like Arizona and other parts of the country, there's a huge market for it. And in fact, there are many treatment plants that treat their waste and none of it gets discharged to receiving waters. It is 100% used on irrigation. Another major product, biosolids. It is a valuable fertilizer product that is really key for carbon sequestration. And renewable energy from our digester process, where we create a biogenic biogas, which can be used subsequently for green energy purposes. And finally, there's a huge amount of research and other facilities throughout the country and the world who are pulling off products from the waste stream. Phosphorus is a fertilizer that, again, can be pulled off the stream. There's also people testing ways to retrieve paper fibers and actually recreate paper. There's a whole list of stuff that is really kind of an exciting exploration for those in our industry. So I'm going to walk you through, imagine you're at a treatment plant, and we're going to walk you through some steps here. We've got some cool videos, but I'm going to walk you through this flow diagram. And then there'll be some cool pictures to look at after this. So I talked about the inputs, which is from the cities itself. You got your rainwater coming as well as your regular wastewater. There's, like I said, a series of upstream pumping stations that get to us. And then we've got this separate food waste process right here, which we'll talk about a bit later. But the first step is basically this preliminary process that we do called screening. And if anybody wants to see some scary videos, we could send links to you to show what people should not flush into the toilets. Not only does it cost a lot to take it off the screens and take it to the landfill, this is public dollars that we're spending. It's about $20 million a year. It clogs equipment, and we spend a lot of time maintaining and repairing and trying to fix stuff because of the huge list of things that people flush. We pump from there through the treatment plant process. We raise the elevation. The first step is primary treatment, where we get I'm going to call it the floaters and sinkers tank. It is a long tank where we'll get grease to float to the bottom and solids to sink to the, grease to float to the top and solids to sink to the bottom. Second step there is the secondary process that I mentioned, which is conventional activated sludge, where we create a biological community to further break down the waste. And then we go to a final settling tank. We reuse some of that bacteria, and we take some waste sludges, the waste solids that go to the solids processing component, which are digesters. Digesters work just like your stomach. And from there, we get solids, biosolids, that is a valuable fertilizer product. We get green gas, and we could create heat or electricity. And finally, from the water side, there's a disinfection process. And if you look to the bottom right-hand side of this diagram, you see a very happy whale in the harbor enjoying the clean water. I went through that really fast, and I think we're going to send people these slides. But the best part is we're going to show you a little bit deeper dive into each of these. I think we have 5 stops. So this, the next set of slides, you're going to see what you would see sort of on a physical walkthrough at the treatment plant. And I will kind of repeat what I just said about how each of these processes work, but I will do it more slowly and thoughtfully so that I can provide a clear picture of how this works. Okay, so I don't think we have sound, which is probably a good thing. I talked about that first step, which is screening. Okay, we have bar screens, and if you see, and the bar screens are basically that, they're bars, and then we send these rakes down. This is the influent comes to this low-level tank. There's the bar screens, and the rakes will come and scrape the debris from the bars and dump it into this conveyor system. And you just, if you look closely, it's impossible to miss. That is what gets stuck in the screens. 80% of that is quote unquote flushable wipes. If you learn anything from our time today, you and all your friends and your family will only just flush 4 different things. Okay, everyone paying attention? Get your pens out. Poop, pee, puke is okay, and toilet paper. No other kind of paper. But Pam, does facial tissue break down just like toilet paper? Guess the answer, no. Paper towels, no. Baby wipes, no. But it says flushable on the box. They lie. It's not flushable. It gets out of your toilet. It does not break down in the system. We're having a big fight with people who produce flushable wipes. So enough of that. Y'all need to see this in real life and only flush the 4 Ps. And if not, I will send you to this treatment plant to pick out everything that you flushed. It is not in that list of 4 things. But Pam, what about floss? Is floss in the list of 4? No. Floss gets tied up with this stuff. Okay, I'm a wastewater person. This stuff is nasty. Don't do it. And if you want to see some real good videos, we could send you a link to this Cheddar video and also the Verve people, I can't remember what they are. They did a really good job on the flushable quote unquote wipe stuff. Enough of that. You can tell I get a little excited. I think it goes step 2, which is, next slide. Those videos are working well. I mentioned this, primary treatment. So this is the first stop, and they're just long, narrow tanks. And it's a just slow-moving environment where allows the greases to float, the floaters, and grit, settable solids, inorganic solids to sink and at the bottom of the tank. And then we have these scrapers that move along and take out, move the grease off the top and then the grit off the bottom. That little end is the grit removal. It's not really primary treatment. But anyway, when I talked about those first plants that were built in the late 1800s, they basically were this. They were like simple primary, probably a lot smaller than this, but a primary treatment tank with disinfection that did an okay job for the day when they put those in. But next slide. They're more primary. Okay, so now we're getting to secondary treatment. Okay, this is what's amazing. Think about this. If a bear poops in the woods, what happens? There's soil. There's nutrients from the leaves that are falling and the foliage around it. There's oxygen. And over time, depending on the conditions, that poop becomes fertilizer for the forest. It's brilliant. There's nutrients, there's air, there's bacteria. So we basically take those same ingredients and put it and control the environment through air, through retention time in the tanks, through the concentration of microbiology in the tanks relative to the food, the waste coming in. And we do that process just like a bear poops in the forest. We do that in a matter of hours instead of days or months or weeks, but ultimately ends up in the same place. That we take that organic material and break it into a usable compost and a green gas. So this is really the heart of the secondary treatment process. And it's quite amazing when you think about it, you know, people being able to figure out that we could speed up Mother Nature by engineering it in. Next, I'm going to try and speed up because I don't know if people are getting bored. This is a real cool picture of the bacteria that work for us. And again, we set the conditions so that these beneficial bacteria show up and do the job. And I don't think the video is working, but it's very cool. When you go to the treatment plant, you should also go to the lab, and we should send you a video of this. But this is the bacteria, we call it sludge, activated sludge, that mixes up and treats our waste. Next. And then we go to disinfection. So there are some pathogens that may be remaining in the final water. After the secondary treatment, we settle it out and we take the water off the top of that, which is this clean stuff. We just add a little household bleach, basically household bleach strength stuff, and send out the final clean water. The solids off the bottom of final tanks either go back to the secondary aeration basin to use the bacteria over again, or it goes into the solids treatment process. Next. And I think we're going to talk about solids processing now. These are digesters. If you've been to Newtown Creek, you've seen them. If you've driven on the LIE, you've seen them. These work just like your stomach. There's no air in them. And we create another environment where anaerobic bacteria break down the solids, and we create from there the biosolids product as well as methane biogas that can be used beneficially. Two major components to our sustainability and energy production. Next. Oh, I talked about the boats. And why do we have a Navy? So I'm not going to talk about the past. I'm going to talk about the present. When we put in the final step for the biosolids, which is dewatering, so we get this fairly liquidy looking biosolids out of the digesters. This needs to be dewatered, and then we make like a cake. It's very soil-like process. And so that cake comes from centrifuges, and we need to get the biosolids from the digesters to the centrifuges. By economy of scale, there's only 6 plants that have that dewatering final step. So we have to transfer the digested solids from the digesters to those final plants. Some plants transfer those solids, like the ones in Staten Island and also in Jamaica Bay, by pipes. So the sludge from Jamaica Bay treatment plant goes to 26th Ward, for example. Some of them, we put the sludge on boats and we transfer it from one plant to another. For example, at Newtown Creek, we're going to load a boat there and take it over to Wards Island, and vice versa. It's a really amazing logistic marine environment deal. I think we're the only one in the world who uses these boats, and it's working out fine. It's like, again, a challenge, especially with 14 plants and only 60 watering facilities. Next, what do we got? Oh, so here's some real fun stuff. We talked about wastewater resource recovery. You've seen this already. All right, I want to emphasize a couple things. One, food waste. Food waste is digestible in a digester. We have a connection with waste management. They take food waste from various sites in the city, and they create a slurry that goes directly in our digesters. At Newtown Creek, can you step back a little bit? Okay. All right. Maybe, okay, but let me, before I go to the next slide. So we're going to talk a little bit more about food waste. But the other component I want to talk about was the green energy production from the biogas in from the digesters. And I think there's more slides on this, so I think I'll just go, because Carlene, you were right to advance that slide. Let's talk more about food waste. Source separated organics. They are collected by DNSY. They're also mandated that a lot of commercial facilities in the city separate their food waste. We're trying to keep food out of landfills. Lots of good reason to do that. I'll let DNSY explain more about why, but it is best not to put food in landfills. And if we separate them from the waste stream, I mentioned that waste management, we work with them. They make a slurry, goes directly to our digesters. I would like people to think about this for a minute, and that is this. We at Newtown Creek have about 500 tons, actually it might be as much as 1,000, of excess capacity in our digesters. It could be up to 1,000, but let's just say 500. The city has 14 sets of digesters because every wastewater resource recovery facility has digesters. Not all of them look as cool as the Newtown Creek digesters. So people think they're just tanks, but they're doing the same thing. We have 14 sites, and of that, we have 75 individual digesters. So if we invested well and invested right through the city, we could take a lot more food waste. Currently, Newtown Creek is taking about 200 tons a day. Like I said, it could take up to 500 or 1,000 tons a day of food waste. The city produces about 2,000 tons a day of commercial and 2,000 tons a day of residential food waste. I know it's logistically challenging, first of all, to get people to separate their organics, but we could, within the city itself, build enough digestion capacity to take 100% of the city's food waste. And that's freaking amazing, because we're keeping, we're taking the resources locally and using them locally and creating the benefit locally. Next slide. Okay. So why are we doing this? We're doing it because it's the right thing and it's best business to utilize our resources from wastewater to develop the green gas and utilize it. But we're also required to. So I love that we have pretty aggressive carbon and energy goals. Here's the list. And these came from, the planning in the city over the last 10 years or so have been driving towards this. And I can't remember the last time the last goals came out, but under the last administration, these came out. Okay, so 80% reduction in greenhouse gas emissions and achieve carbon neutrality at the wastewater resource recovery facilities as a network by 2050. We have a 40% reduction target by 2025 and 50% by 2030. 20% reduction in energy uses by 2025. And then we do have another goal to meet energy neutrality, and you could read these list of things here. It's a matter of increasing efficiency and increasing the production of green products. Challenging. And we have made progress in this direction to date, but there's much more intensivity that needs to happen. What's my next slide? Okay, so this will go into a little bit of the strategies for carbon and energy neutrality. For all these facilities, we are using the gas internally to generate electricity to run pumping systems at North River, for example. We are installing solar at treatment plants where it can be easily retrofitted to the existing infrastructure. We have 1.2 million megawatts down there at Port Richmond on Staten Island. Wards Island there's a 5 megawatt solar photovoltaics coming in, I believe in 2024. So very soon. There's also a study of how we can expand that throughout the agency. I remember what I was going to say about energy. I'll say that in a minute. Improving our process equipment. So a lot of our equipment is old, and as we upgrade, we look to put in equipment that does the same performance at much less energy consumption. Utilizing our biogas, 100% to beneficial use. We're not quite there, but we're getting close to that achievement. Putting gas back in the grid that can be used for local heating and even cooking in people's homes. There will always, as the city electrifies, however, there will always be a need for a certain amount of green gas for niche markets like, for example, hospitals and other places where they have to have combustion in order to sterilize equipment. The solids that are generated at treatment plants will always be generated because of part of the process, and we have the opportunity and we sit in a good place to utilize those green resources. I also mentioned food waste to co-digestion, which is something that is ongoing. So I wanted to talk a little bit before we go to the next slide about energy. And we are big consumers of energy. And first of all, you have to pump the waste to the treatment plant. And then in the treatment plant, because we utilize gravity as much as possible, the water enters the treatment plant at a pretty low level, and then we pump it up to a higher level and have it flow by gravity through the treatment plant itself. So pumping water is just a reality of topography. We can't not pump water. We can try and more efficiently pump water, but the actual physical energy of moving it from a low point to a high point takes energy. The other big consumption part of wastewater treatment is the aeration. We have to put air into those secondary basins to create the biology that breaks stuff down for us. That's another one. And then I was going to have another one to add to that but I can't remember, but let's move on. Oh, wait, before we get there, back. Here's something that's really cool. This one on the bottom, innovative renewables. The wastewater coming to the plant is very warm. So now people are taking heat off of the influent in a district heating localized method where a neighborhood could be heated from the pipes in the street. Same thing at the treatment plant. We heat the solids that go to the digester. The digester that works just like your stomach needs to be heated to 98 degrees, just like your stomach. We utilize heat in the wastewater process to do that. And we could pull heat off of that and actually reuse that within the plant. So we're actually constantly looking at ways to reduce not just our energy consumption, but that of the neighborhood around. Oh, the last thing I was going to say about energy consumption is centrifuges. So the dewatering process, we have to take water out of the biosolids to make that final cake too. Another big energy thing. So this is a huge map of opportunities and innovation that we're utilizing to meet those really aggressive carbon and energy goals that I just mentioned. Okay, more about biosolids. Biosolids are magic. It is a very valuable fertilizer. It is regulated, highly regulated, more regulated than what you're going to find if you go buy steer manure at Home Depot. Very high level of nutrients. They can be used in forests and farms and actually sequester carbon. It's a huge component to offset the carbon of an industry. When I worked in Seattle, we actually ran our wastewater utility at carbon neutrality because of the value of carbon sequestered from the green gas production, but also from the land application of biosolids. There's a lot of science behind this. It's really cool when you look at we used to set up these plots with farmers where you had biosolids product, regular fertilizer, and no fertilizer. And the biosolids product, much more valuable than the inorganic fertilizer because not only just the nutrient value, but there's micronutrients that you don't get in inorganic fertilizer, and the ability to retain water in that biosolids matrix is so much better that the farmers don't have to irrigate as much, and it just retains a better soil matrix for those plants. What else do we got here? So this is about the value of carbon recycling and carbon sequestration. And if you look at, and this is a little complicated, I guess I should have reviewed this before I looked at it, but in the 2030 timeframe, I would say this, yes, we're about 70% landfilling now of our biosolids. Yes, so 30% beneficial use. By 2025, just around the corner, we want to be about 60 or so percent to beneficial use, and our 2030 goal is zero waste to landfill. So that means out of the landfilling business and using the solids beneficially. Next, I think it's some cool pictures. Here we are, some very nice biosolids products. Oh, and there you have your graph of a planting bed. All right, next. What do we got? All right, so this is where we get to a little bit more fun. I think that might conclude sort of the super technical, to the extent that it was, version of this presentation. And now I'm just going to talk about a little bit more of our history and our trajectory of where we're headed. So one of the amazing things is we built these treatment plants, and like most cities, they built these plants away from where people lived, because back in the day, first of all, there wasn't odor control. And you wanted where there was a big chunk of space. And you could see in 1950s on Coney Island, Jamaica, just two examples we put up here, they were away from where people lived. And nobody really knew they were there or cared very much. If you look at Coney Island today and Jamaica, different story. If you're standing in the middle of the Coney Island plant, you can see the apartment buildings right across the street. If you're at Jamaica, well, one side is kind of the airport, but there's a lot of homes and businesses very close to there. So it's a very different paradigm now. We are neighbors. We're located with neighbors now that did not exist before. We have a responsibility to not only be a good neighbor, but to be a proactive, excellent neighbor and provide the full breadth of opportunities that the wastewater utility as a business can. So I think with that, well, let me just mention one other thing. If you look at the 14 plants and you look at what the city defines as environmental justice communities, since there's such a huge percentage of New York City is really an EJ community, now with the population around each of the plants, they're all in EJ's communities. There's no differentiating between each of the plants anymore about, well, this one's in an EJ community and that one isn't, because it pretty much is there. So we got to take that into consideration as well.
Pam, if you don't mind, can I just point something out quickly? When you look at these images, these rectangular structures that you can see, especially in the top images, but also in the bottom ones, are the primary and secondary settling tanks that we were talking about earlier. So just gives you a little visual of how large those are and how large these facilities are.
Yeah, and that's a good point. I mean, if I'm trying, first of all, the scale is challenging because the pictures aren't the same scale. So the plants are actually take up more space than they did back then because we have extra tankage that was not required in the early days. But they are very land intensive, and with the need for housing, like I said earlier, there are people living right next door to us now. Intensive process. These are industrial processes that I'm talking to you about. Okay, so let's talk about Rikers. This whole thing was not really about, let's talk about the feasibility study, but I just want to just kind of end on the beginning of the feasibility study. So the Rikers Island feasibility study is going to look at these 4 plants that are on the Upper East River, which are Ward's Island, Hunts Point, Tallman Island, and Bowery Bay. And if you look, you can actually see Rikers sandwiched between those 4. It's significant to look at the drainage area for each of these. The Ward's Island drainage area, and my cursor is not going to work, I don't think, but takes in this northeast part of Manhattan all the way to North Manhattan, which is a huge chunk. It has over 1 million people. It is a bigger treatment plant than most treatment plants in the entire country if we only had Ward's Island. Is there, okay. So anyway, this is. I'm confused if somebody's asking a question or something. Let's hold off on questions till we get there. But I just want to point out that's 1 million people. Hunts Point, it serves over almost 700,000 people. Again, a very dense part of the city and a huge drainage area. Same with Bowery Bay, which is almost 1 million people down here, and Tallman Island, a little smaller population served, but a very dense part of this, because every part of the city is dense. Okay, so these are located in communities. Let's go back, please. These are located in communities. You saw, I walked you through the industrial processes required to treat wastewater. There's limited opportunities for each of these existing facilities to expand or to facilitate upgrades or to be modernized with modern technology. That is very, very challenging. And go to the next slide now. So there is what what this group is interested in, which is we are at a point of looking at consolidation. It is really a generational opportunity that will, if it pans out, 1 up to 4 of these wastewater resource recovery facilities can have some of their operations relocated to what's going to be freed up at Rikers Island. So the advantage, just strictly from a wastewater professional perspective, is we have a new geographic area, which would provide a clean slate, a clean canvas to create wastewater resource recovery technology that would literally be impossible to modify our existing plants in any reasonable future to get there. It would really be able to leapfrog us from an old technology that we're trying to modify to like technologies of this century and intentionally build that for the communities, for the entire city for 100 years to come. So it is an incredible opportunity just strictly from the wastewater performance and treatment process. There's a lot more that goes into it and a lot more that is very valuable, which is this potential to modify what are those existing facilities should some of the treatment processes be moved to Rikers Island. Now, I have to say, you saw the drainage areas that I showed you. We're still going to have to get the flow from these existing points where all the flow is discharged to now to the island. So there needs to be retained some conveyance capacity at each of these sites, some treatment capacity, some opportunities for advanced treatment capacity that we currently don't have, particularly potentially for combined sewer overflow control. But the sort of this side 2 of this generational opportunity really is freeing up space for communities, and it's part of environmental justice response, but also as we come out from being underground about what we do, really providing a full scope of opportunities for people in terms of economic justice, in terms of jobs, in terms of training, in terms of education, in terms of just providing that integration with our local communities that have been challenging to date. And I really think we could do a better, a better job at that. And I think this is my last, well, no, there's one more, but I just want to just close with the, well, let me go to the next slide and I'll have some statement at the end. But so the consolidation feasibility study is being led by Kathleen Esposito for the wastewater resource recovery side. There's a parallel effort going on for energy, which I think Kathleen's going to mention. Here's, it was driven by the wastewater side. It's the right thing to do. And by the way, there's a local law that says we have to do it. So that's been giving us the impetus and the support to move forward on doing this analysis. Now, I have to say, like I said earlier, from the wastewater side, it's a generational opportunity, but I want us to all think about this as a social opportunity, a triple bottom line opportunity, which is environment, finance, social equity. And that is really the driver for this project. It's really a community project at this stage to analyze it and see where we might end up towards that trajectory in terms of affordability, reasonability, and technical ability for it to be established. So this is the layout. We're somewhere in the process. I think the feasibility completion is scheduled for October 2023, and it's a very exciting time to be in our industry. And I am glad that I think we have 50 people excited about this and participating and being partners with us as we move towards this feasibility study analysis.